Right, got the AS paper 2022, question 5. This is the sort of the non-linear relationship. So this is actually an exponential relationship because you've got the t up the top. We've got it as a log equation there. So mass A, the algae in a small pond, multiplied by the equation A, PQ to the power of T. P and Q are the constants, so the numbers we're going to try and find. T is the number of weeks after the mass of the algae was first recorded. Data recorded indicates there's a linear relationship between T and log to the base 10 of A. If it said log 10 of T and log 10 of A, then it'd be P T to the power of Q. It'd be the sort of power relationship. This is an exponential one because it's T and log the base 10 of A. We're going to use this relationship to find a complete equation for the model in that form. So one way to do it is to start off with the relationship. We don't know what P and Q are. If we do the logs of both sides, because this is the log equation. These are logs base 10, of course. And then I can break this side up into the log of P plus the log of Q to the power of T. I can bring the T down and I can write it like this. So this will be log of Q multiplied by T. I need those brackets around it because I don't want to say log Q, the log of QT. It's the log of Q multiplied by T plus the log of P. Then I compare it with the linear relationship. I've got log of A here. I've got something times T here and then the log of P. So comparing it, I can see that the log of Q is 0.03. So the Q is 10 to the power of 0.03, which is 1.072. The log of P is 0.5. So P is 10 to the power of 0.5, which is 3.162. And there's my full relationship. Some people prefer to go the other way and start with the relationship that we have and get it into this form. So if I do, I really do 10 to the power of both sides, really. If the log to the base 10 of A is equal to this, A is going to be 10 to the power of this. Then I can break it up using the power rules. This is 10 to the power of 0.03 multiplied by 10 to the power of 0.5. And then with the rules of indices, I can write this as 10 to the power of 0.3 all to the power of T. And then I've got 10 to the power of 0.5, which is the 3.62 times this, which is 1.072 to the power of T. Reference the model, interpret the P and what the Q is. Well, the P is the A when T is 0, because Q to the power of 0 is going to be 1. Mass says the initial mass in kilograms in the pond. And the Q, they call it the ratio of algae from 1 week to the next. It's really the factor is multiplied by each week. So going from week 7 to week 8, what does the mass multiply by? And each week it's multiplied by 1.072. Finally, according to the model, the mass of the algae when T is 8. So if T is equal to 8, we just put 8 into our formula. Gives us about 5.5. Number of weeks extra the mass to reach 4.4 kilograms. So here we go. 4 is equal to 3.162 times 1.072 to the power of T. Then divide by the 3.162. And then you can take logs to the base 1.072 in your calculator, and you get about 3.4. And one reason why it might be realistic, I'll show you what it says in the mark scheme. Seasonal changes, there are different things that affect the growth rate. So it's a small pond, so there's only a certain amount of growth it can do before it gets too crowded. Might stop growing for some reason, might get filled up, I don't know. And some of it may die or eaten, something else will affect it. Something, well, then they wouldn't accept though. If you just said there could be other factors affecting the amount of algae, it's too vague as far as they're concerned. And just saying something, the mass might change is no good either. You got to say something specific about the model.